Hi and welcome back to our video lessons. We're going to go through some selected problems and take a look at particular concept applications and some of the mathematical formulas you're going to have to use in these problems. The first problem I'd like to take a look at is number 1 from the work packet that we were using. We're going to use the data tables. I'm going to look at the front page of the reference table. We want to look at values such as the Coulomb and how many electric charges are contained in it. This is the essence of this problem. So let's take a look at it. You have the two identical sized metal spheres on insulating sands shown in this position, and they have 4 microcoulombs. If you remember in the last video, I said that sometimes the Regents uses the symbol micro, and sometimes they spell it out as 10 to the negative 6. So here they've done that. They want to know what happens when you touch the spheres together and then you bring them apart, and they want to know the total number of excess electrons on each sphere. So the idea is that you have to go to the reference table and you have to know how to convert the number of coulombs into the number of elementary charges. And in our last lesson together, we discussed a dollar and penny relationship. So the coulomb is like the dollar, and it has 6.25 10 to the 18th electron or elementary charges as its penny. It's not as easy as a real dollar, which is 100 to 1. This is 6.25 10 to the 18th to 1. Nonetheless, with the same idea as we would say how many pennies are in $3 or $1.75, we would say how many electron charges are in so many coulombs. Or, in reverse, so many coulombs has how many pennies or electron charges contained within it. And in this case, you can see that when the spheres touch, first they share all their electrons back and forth, and then the average number times the elementary charge ratio gives you the number of excess elementary charges. So you had -8 and -4 microcoulombs. So that gives you -12. Divide that by 2 to take the average, and that's where you get 6 times 10 to the -6 coulombs, and you multiply that by the conversion, 6.25 10 to the 18th elementary charges per coulomb, and then this product gives you the number of actual charges for 6 microcoulombs. So this would be something like, say, $600 is how many pennies? Okay, 6 microcoulombs is this many 3.8 10 to the 13th excess electrons. All right. That's how this one is solved. Let's move on to another one. In problem number 2, it says 2 points A and B are located within an electric field produced by a -3 nanocoulomb charge. So there you go, nano. You have to know what a nano is, front page of the reference table. Point A is 0.1 meter to the left of the charge, and point B is 0.2 meters to the right of the charge, as shown in the diagram below. Let's take a look at that diagram. Compared to the magnitude of the electric field strength at point A, the magnitude of the electric field strength at point B is, and then they give you 4 choices. So let's take a look at what we have first of all. Here's your 3 nanocoulombs right here. This is the charge in which we're referencing our distance. So point A is 0.1 to the left, but point B is 0.2 to the left. So the strength of the field depends on the distance, really the inverse square. So what we have is 0.1 to the left and 0.2 to the right. 0.2 is double the distance away. So what they've done in a problem like this, instead of having all the charges on the same side of the source charge, they're putting some charges to the left and some to the right. So in general, here's the derivation. From the reference table, we know that E is F per Q. So the force per unit charge, that's what defines an electric field, and that is a type of acceleration. So a source charge's force is KQ on Q2 over R squared. That is the strength of the force anywhere around in the field around that source. So this is the Q that gets canceled with one of the Q's in this formula. So the strength of an electric field is KQ over R squared, where Q is the source. Now, if we double the distance, notice I have this highlighted right here. If we double the distance, 2 squared is 4, R squared is R squared. So you have KQ over R squared. That's the original formula for electric field. And that's why E shows up here. And then, of course, 1 over 4, 1/4. So 1/4 is great. So if you double the distance, you quarter the field intensity. Okay, let's look on to another one. Here's another question about negatively charged metal sphere and the electrostatic force that pushes on a test charge. This question asks, what is the magnitude, meaning the amount, and the direction of the electric field strength? The electric field strength is very similar to the gravitational field strength. The idea is there's a degree of acceleration experienced by the charge in this region. So this is a straight math problem. E is F per Q. The force was given as 6 × 10⁻⁵ newtons. That's right here. And the charge that's being acted on is 3 × 10⁹ of a coulomb. That's the test charge, and you see it's a positive value. So when you do the math, you get 2 × 10⁴ newtons per coulomb. So an electric field is measured in newtons per coulomb, force per unit charge. A gravitational field, gravity, would be newtons per kilogram, which still means acceleration. So this is one of the concepts I want you to always remember, that electric fields accelerate charges. Now, the choice is number 2, because the direction is towards the sphere. Why is it? Because the test charge is positive, but the sphere is negative, so they're attracted to each other. And since the test charge is so small, it is attracted to the negatively charged sphere. This is very similar to an Earth analogy. This test charge would be like Newton's apple, and the Earth is this large source of gravitational attraction. It pulls the apple to the surface of the Earth. Well, this test charge is pulled to the surface of the sphere.